Welcome to Pre-Calculus Section 7.4 in our Conics series. This video is on ellipses. For any ellipse, you have two what we call focal points that lie on the long axis of the ellipse. And if you can imagine a string attached at each of these focal points and stretched out to reach a point on the rim here on the ellipse itself, and let's say you put a pencil in that and you drag that string all the way around, you'll be able to trace your ellipse. So the sum of the distances between the focal point and any point on the rim, so this D2 and this D1 are always going to add up to the same amount of string, basically, to the same distance D. All right, so at any point along the outside here, that string will fit. Okay? So it's always going to be a constant amount of string, that whole red length right there, if we think about it as a piece of string. With the pencil inside that point there, drag it around, you'll be able to draw the shape of your ellipse. So that's always a good visualizing tool. So the center of the ellipse is obviously at the center, right? So then we've got your long axis, which we call the major axis, your short axis, which we call the minor axis, and then the end points of your major axis. These are, a singular word would be vertex, vertices would be the plural of vertex. And then on the minor axis, the endpoints would be called the co-vertices or the co-vertices. People say it different ways, which is the plural of co-vertex. So these, and then there's one more thing. The foci, which is the plural of focus, are always going to lie on the major axis closer to the end than to the center. Now we can either have a horizontal ellipse, which is long in the x direction, or we can have a vertical ellipse, which is long in the y direction. So typically, these two here actually are shown centered at the origin. Many times we'll have a problem where we don't have a center, 0, 0, that'll have some translation. So you'll have some HK. But looking at these two general diagrams here, we can see that your distance from this point to this point, if this is A and this is A, your length of your major axis would be 2 times A. The length of your minor axis would be 2 times B. All right, and then if it's long on the Y, you've got 2A this way and 2B this way. All right, and then your foci are usually described by the letter C, and those lie on your major axis. So vertical this way. Once again, they're given by the distance C, and they would lie on the major axis. So A, B, and C are the letters A for the major axis, B for the minor axis, and C for the foci. So the standard form of an equation of an ellipse would look like this. Here it says for positive unequal numbers, A and B, the equation of an ellipse with a center HK, so this is an offset, like with the circle, is this equation here. So in this equation, your A and your B are both positive numbers which are not equal to one another. All right, so we're going to do some work with getting our equation into this form if we start out with general conics form. So that'll be the first step. General conics form for the equation of the ellipse will have both the x squared and the y squared terms present. They'll be separated with a plus, and it will have unequal A and B. So A will not be the same number as B for an ellipse. In a circle, the coefficients A and B were equal. In an ellipse, they are not equal. So the essential terms that help you distinguish whether you have an ellipse or not are you going to have both squared terms, you're going to have a plus in the middle, and the A is not equal to the B. Sometimes these terms will not be here, but these always will. That's how you know you have an ellipse. So to write the equation of an ellipse in standard form, these are the steps. You group the same variables together on one side of the equation, and you position the constant on the other side. You complete the square in both variables as needed, and then you divide both sides by the constant term so that the constant on the right side of the equation becomes 1. All right, so these are the steps, and they're not going to make a whole lot of sense until we run through it a couple times. So we're going to do 2 complete examples. For each of these examples, we're going to find the following items, and we're going to sketch a graph. We'll find the center, the vertices, which are the endpoints of the major axis, the co-vertices, which are the endpoints of the minor axis, the length of the major axis, the length of the minor axis, and the coordinate pairs of the foci. Remember, the foci lie on the major axis. So we're going to do 2 full examples. So here's example 1. So we're given our equation in general conics form, and like I mentioned on one of the other slides, you're going to have your x squared and your y squared terms present. You'll have a plus in the middle, but the coefficients of your x squared and your y squared terms will be different numbers. So let's go ahead and set it up to complete the square. We're going to need to complete the square twice. So we're going to group by variable. So we have 16 x squared, and I'm going to get my other x term. I have 64x, put those together. And then I'm going to group my y terms. I have 9y squared plus 18y. And I'm going to move my constant term over to the other side. So I can see here that I have 2 x terms and 2 y terms, which means I need to complete the square once for the x's and once for the y's. So we have coefficients, so we treat those coefficients by taking them outside the parentheses. So I have to figure out 16 times some term here will equal 64x. Well, if I take 64 and I divide it by 16, I'm going to get 4. So I put 4 here. Then I check it. 16x squared checks. 16 times 4x checks. And then I put my balancing blank, which I need to engineer my perfect square trinomial. Here I also have a coefficient. I'm going to treat it the same way. Outside the parentheses, this time I'm going to divide 18 by 9, and I'll get 2. So that would be 2y plus my blank equals 71, and then I need 2 balancing blanks. All right, so let's check that. 9y squared, good. 9 times 2y, good. So now I take my 4 in the middle, I divide it in half, which is 2, and I square and I put 4. All right, let's wait a minute and figure out what the other one is. So I take 2, divide by 2, and I get 1, square it, and I get 1. Now what's happening here is because of this 16 on the outside, I have to multiply that by 4 to figure out what I need to put over here. I did not just add 4, so I can't just put 4 here. I've added 16 times 4, and that's 64. So I didn't just add 1 here, I added 9 times 1, so that's 9. So now if I add all those numbers up on the right, I will get 80 plus 64, that's 144. All right, so I've got 16. Now I'm going to write my perfect square trinomial in factored form for both of these here. I've engineered them to work to be factorable like perfect squares. So I've got x plus, so remember, square root of 4 is 2, plus goes here, x goes here, so y goes here, plus goes here, square root of 1, which is 1, goes here. All right, now this last step right here on the slide where I give you the steps says divide both sides by the constant term, that's the term on the right, so that the constant on the right becomes 1. All right, so that's how we get this standard form here. You're always going to have a 1 on the right-hand side. So let's go back to here. I'm going to divide this out so I equal 1, which is what I want for standard form. So I'm going to divide here, and I'm going to divide here. So now I just reduce these fractions. 16 goes into 16 once. 16 goes into 144 9 times. 9 goes into 9 once. 9 goes into 144 16 times. So now I've got my form that I want. X plus 2 squared with a 9 on the bottom. Y plus 1 squared over 16. And let's move the 1 over closer. Equals 1. So this is standard form for the ellipse. So make sure you took down every step that we did here so that you're able to do this on your own when you're given an equation by looking at your notes. All right, so I'm going to make some room for myself on this page by keeping only the equation. All right, now we examine the equation to see which way this ellipse is oriented. So what you're looking for is where the bigger number is. So basically, if you think about these as radii, the larger radius is in the y column here. This is the y column. And the smaller one is in the x column. So this particular ellipse is long on the y, and short on the x. All right, so this 16 is equal to your a squared, and your 9 is equal to your b squared. That means 4 is your a, and 3 is your b. So if I look back at this slide, your a is the dimension from your center to the end point of your major axis in both directions. This is also the distance a. So this is a, this is a, this is b, and this is b. So now we know a and b. So the next thing we want to do is get our center. So our center is taken from these factors up here. So opposite sign, so that's -2. Opposite sign, that's -1. So -2, comma, -1. So let's put it on this graph over here. Here's my center. Next, I'm going to look at my a dimension, and I'm going to go long on the y. So my a dimension is 4. I'm long on the y. So I'm going to go up 4. 1, 2, 3, 4. One endpoint, and down 1, 2, 3, 4. This is my other endpoint. So this endpoint here is -2, 4, 1, 2, 3, 4, 3. And this one down here is -2, comma, 1, 2, 3, 4, -5. All right, and then I'm going to go on the short dimension out by this amount 3. So that's going to be 1, 2, 3, 1, 2, 3. So this point here would be 1, -1, and this point here would be -5, -1. So I'm going to write in my vertices, which are the ones on the major axis. So that's this point and this point. So I've got -2, -5, comma, -2, 3. And my co-vertices are the endpoints of my minor axis. So I've got -5, -1, and 1, comma, -1. Next, we need the length of the major axis. So the length of the major axis is 2 times this dimension A. So A is 4, so this is 4 and 4, that would be 8. And then the length of the minor axis is 3 plus 3, which would be 6. So that leaves one more piece of information that we need, and that's the foci. So we need to do a calculation to figure out what the foci are. So the foci lie on the major axis, and they are points. So I'm going to sketch in my ellipse right now. All right, and then I'm going to make some room to do my focus calculation, my calculation of my foci. So to calculate my foci, there's a little formula involved. So the formula says c squared is equal to a squared minus b squared, where a is bigger than b. And I'm just going to give you a heads up. It's something I've noticed, and this is a discrepancy from book to book, teacher to teacher. Sometimes the illustration of your ellipse will not always call the long axis A. It will say A always goes with the x's and B always goes with the y's, but that is not as standard as saying A is always bigger than B. So A is always the length of your major axis and B is always the length of your minor axis. So be careful in some of the homework problems that you're doing exactly using the letter that they're using to describe either the major or the minor axis. But this is the way I teach it. I always teach it one way, where A is always bigger than B. So this is the formula that you use to find C. So in our case, A is 4 and B is 3. So 4 squared is 16, right? Let me just write it. And then 3 squared. So that's C squared. So that's 16 minus 9. 16 minus 9 is 7. So if I take the square root of both sides, I'm going to get a radical. So that length C is root 7, which is approximately 2.646. But we usually leave it in exact form. This is more standard rather than a decimal approximation, but just for graphing purposes, if I wanted to get my foci drawn in on the major axis, I would be going up by the square root of 7, starting at my center. I'm going up by the square root of 7, which is 2.646. So I'm going to approximate where that is. And the same thing here. So these are my foci right there, right on the major axis. And the coordinates of the foci are written like this. So they're going to be coordinate pairs. So they're always going to, in the case with this orientation, you can see that they have the same x value here, -2. The x value of here is -2. and also here. So I can go ahead and write -2 for my x value. All right, and then for my y value, my offset is, if you want to think about it this way, I have a starting point of -1 and going to go up by √7 and then down by √7. So this is -1 up √7. This is -1 down √7. And we just leave it like that. That's how you write your y coordinate here. All right, so we've done it. This is all the information that we need. So I've highlighted all the stuff that we were looking for. We're going to do one more example. All right, so here's our second example. It's given to us in standard general conics form. The reason I know this is an ellipse is because it's got both an x squared and a y squared term. They have different coefficients, and there's a plus in between. So I need to complete the square twice. So I'm going to set this up. Whoops. So I'm going to organize. So I've got my x's, and then my y's. Now make sure you're writing all this down just like I'm doing it here. And then I'm going to move my constant to the right-hand side. Now I'm going to complete the square twice. So I take out my coefficient, and then I check to make sure that I'm getting the same two numbers. 9x squared, yes. 9 times 2x, 18x, yes. Put my balancing blank in. Take out my coefficient. Now I see 25 goes into 200 8 times. Balancing blank, and then 2 balancing blanks over here. So now I complete the square twice. So 2 divided by 2 is 1. So square that and you get 1. 8 divided by 2 is 4. Oops. Square that and you get 16. All right, now we have to be careful here. We have 9 times 1, so we put a 9 over here. We have 25 times 16, which is 400, so we put a 400 over here. All right, so now let's see what we have in factored form here. We have 9 times x plus 1 squared. X here plus here, square root of 1 here. And then we've got this plus here. We've got 25. And then your factored form. So we've got y minus square root of 16 is 4. And then I'm going to add -184 plus 9 plus 400, and I get 225 for that. Last step, I'm going to divide by 225, so I get that 1 that I need on the right-hand side. All right, so I've got x plus 1 squared, y minus 4 squared equals 1. All right, let's reduce those fractions here. 9 goes into 9 once and into 225 16 times. 25 goes into 25 once. 25, wait a minute. So this 9 times 25 is 225, so reducing this is actually 25 here. All right, so then back over to this one. 25 goes into 225 9 times. All right, so now in the denominator here, I've got 25 here and 9 here. Right, so this is the form I need for figuring out all of my information. So I'm going to go ahead and erase some of this stuff and make some room to record all of the information that we're asked to find. So here's my equation. So I can see from the bottom numbers that I've got an A of 5, which is the square root of 25, and I have a B of 3. Let me just back up a second, just so you can take really good notes. A squared is 25, so A is 5. B squared is equal to 9, so B is equal to 3. All right, notice I'm long on the X this time, and I'm short on the Y this time. And the way I was able to tell that, if the smaller number is with the Y, I'm short on the Y. If the larger number is with the X, I'm long on the X. So this is a long parabola this way. All right, so some people might call that a horizontal parabola. So from my equation, I can write down my center. So I get my center from the parentheses, opposite sign, so -1, 4. So putting that on my graph, here's my center. All right, so I'm long on the X, so I'm going to go out 5, endpoint, endpoint. So these are my vertices. And then I'm short in the Y, 3. So these are my co-vertices. So let's draw them in, the endpoints here. So my coordinates are for my vertices. So I've got 4, 4. So one of my vertices is 4, 4. And then over here I've got -6, 4. Some of the other vertex is -6, 4. So let's write those down. So I wrote the vertices down here. All right, and then let's go ahead and figure out my co-vertices. So they're in line here. So that's your X of -1. So up to 7 here. And then here, -1, 1. So let's write those down. These are the endpoints of my minor axis, and those are called co-vertices. Next, we're going to find the length of the major axis. So the length of the major axis is from here to here. So that's 5 and 5, so that makes 10. And the length of the minor axis is from here and from here, so that's 3 plus 3, that's 6. So I'm going to trace in my ellipse now. So it's long on the X. Now we expect that my foci are going to be along the major axis, closer to the ends than to the middle. So the last thing we got to find are the coordinates of the foci. So there'll be 2 foci. All right, since the orientation of this ellipse is long in the X, I can see that if they're going to lie on this axis here, that they're going to have the same Y coordinate as these 2 points and the center. So my Y coordinate is 4. So I've got to figure out my X coordinate. To do that, I have to use my little equation that says C squared is equal to A squared minus B squared. So that means C squared is equal to 25 minus 9, which is equal to 16. So the square root of c squared is c. Square root of 16 is 4. So that means c is 4 this time, so we have a better behaved number. So I'm going to go out from the center, 1, 2, 3, 4. So here's one of them. And then in the other direction, 1, 2, 3, 4. So if I figure out what those coordinates are, so for the one here, I'm over at 1, 2, 3. 3. And then over here, I'm at negative 1, 2, 3, 4, 5, negative 5. All right, so that takes care of everything that we were asked to find. Let's highlight all of our answers now. All right, so that wraps up our video on ellipses. Now for each of the homework problems, you're not going to be asked to find all of these pieces of information every time. Some problems will simply ask for some of the information. But this gives you a comprehensive approach to any ellipse problem. So go ahead and give your problems a try and let me know if you have any questions.